All right. So as I was looking at some of the things, couple of concerns on things. So let's just look at this. Today's we're going to go on to the next and last of the three sections that the quiz is on. Next Monday, it looks like, is when the quiz will be. I think I said it yesterday, but in case I didn't, it looks like Monday, okay, for the quiz. So optimization here is one of those three things. We have parametric equations, which we'll come back and review that, especially on Friday. Spend some time doing that. But parametric equation was one. And then optimization here is the second thing, and then we're going to go on to the third thing here today. But we're going to continue doing some optimization problems. As a matter of fact, over the next several days, as we do the next thing we're going to do, we're going to mix in optimization problems with it, because sometimes there gets to be some confusion between the two, even though they're not nearly the same thing. They involve derivatives, but they're not nearly the same thing. But what's similar about them is they're story problems, number one, and the other thing is that we kind of have a set of steps to follow with this other new thing we're going to learn too. And so I think sometimes people confuse the two a little bit, but really if you're thinking about what the problem's about, they're not anything alike at all. And what you're trying to accomplish. So if you understand the big picture, that shouldn't be an issue. But anyway, so what we will do as we work over the course of the next several days, we'll be doing some of both kinds of problems. So we'll continue to work on these max-min problems. So we had our steps. We talked about there being kind of this imaginary red line, I guess I called it yesterday, so we'll continue with that theme. But the red line was kind of here, and that was with the idea that above the red line is just getting the problem set up so that we could have a function, we could have an equation, we could have a thing that we're trying to maximize or minimize. And then below the red line is just the calculus steps that we learned in Chapter 2. How do we justify that we have a global max or min, an absolute max or min? And we have to go through those steps, okay? So it's getting these things set up that we need to really focus on. So as we go along, let's talk about number 19. So on number 19, this is one of my favorite problems that we do in here. Maybe it's because I'm a track coach, and it kind of fits in a little bit. When you say, well, track coach, what's that got to do with anything? They were talking about a football here a little bit, weren't they? But it reminds me of a class I took in college, and I'll tell you about that here a little bit later. But they give you this equation, which is for a projectile, which is a little bit like parametric equations, if you remember, when we're talking about a football like this, and if it's kicked, and if you've got kind of an X and Y axis here, right, and we kick the football and it comes back down, and so it's kind of a trajectory kind of thing, which we did with parametric equations. We had an X equation and a Y equation for that particular path of that football. So what we've done, and remember one of the things we talked about with parametrics, if you have an X equals some t's and y equals some t's, that we could combine that, remember, and get rid of the t's, remember that, eliminate the parameter, right? Nod. Yeah, okay, at least some of you nod, please. Okay, so we eliminated the parameter, right, and turned it into just one equation. The difference is we don't know where the ball is at any time, right? That's the advantage of parametric equations. If we had an x equals and a y equals equation, we would know where the ball is at certain times. But at the very least, when we have this equation, we have the path of the football, right? And so x is its horizontal position of the football, and y is the vertical position of the football. So there's a connection to parametrics, although this isn't a parametric equation. This is like we took the parametric equations, turned them into just one equation that had x and y in it. So we have the path of the football. Okay? Thank you. All right. So then they gave you a bunch of numbers to plug in, like 9.8 for gravity and 30 for the initial velocity and 1 for the m. What was the m? The slope. So in other words, the ball was kicked. So the y equals mx part, they're just saying the ball is going to be kicked with an initial angle of 45 degrees. That's what that means. The slope of 1 would be 45 degrees. So we have to have several things. We have to have the initial velocity that the ball's kicked with, like we did with the pitch. And we have to have what angle it was kicked at, and that's the m here. So that instead of doing it as an angle, because it would make the problem a little more difficult, they did it as a slope. Make sense? So I went ahead and I plugged those numbers in. Okay, So what did the question ask them? The question said, how high did the ball rise? Right? Wasn't that the first part of that question? Now again, I'm going to keep saying this. You've got to, we're in the process. I know your head's swimming here a little bit on some of this stuff. But you've got to stop and think, because some of the questions I'm getting from people, and quite honestly, I'm glad you're asking me this questions, because I know there's a lot of you who are not coming in to ask, and I'm guaranteeing, I'm guessing many of you have these questions, but you're not asking. But some of the questions I'm hearing is, well, what do I do? How do I do this? What do I do? And as if you're trying to memorize steps or something, right? Instead of understanding what the question's asking. So when it says, how high does the ball rise? With that equation, and I just drew a picture of it, what am I looking for? Okay, well, y prime would be a good thing to do, but let's back up before that. Why would y prime? Yeah, don't we want, when it talks about how high the ball rises, are we looking for that right there? And what part of that are we looking for? Don't we want the y coordinate of that point? And is there anything on that screen right now that would represent the y coordinate of that point? Right? Isn't that right there, the y coordinate of that point? But then the question is, how can we find that? And then that's why you would think about doing that, right? So those of you that are asking me, well, what do I do? You got to think, what am I looking for, right? Oh, I'm looking for this. Oh, what's happening right there? Oh, the slope is 0. Oh, y prime, right? Look, it's like a max, right? It's like finding the max of this. Okay? So it's like an optimization problem. So I got all these numbers and everything, and I could simplify this a little bit. I could get y equals x minus whatever that big mess is, times 2. 1 plus 1 is 2. I could put that 2 up there. 9.8 times 2 is what? 19.6? Now, at some point, your calculator could help you here. This is 900 times 2. That's 1,800 x squared. I mean, basically, that's the equation, I think, isn't it? They do that right? Again, it's another upside-down parabola, which, of course, we know. So let your calculator do this for you. Do the derivative. Set it equal to 0. And what do you get as your x value? 45.918. Great. 45.918. But and again, so then some of you are you're gonna look at that and say, and you might think that's your answer, right? What do these letters represent, right? What does x represent in this problem? Horizontal distance. What did we just find right there? Right? We just found that, right? The x coordinate of that point. Is that what we want? I don't think they ever asked for that in this problem, did they? Right? What do we want? We want the y. Now, if we'd already thought of that, see, we'll know what to do, because we'd already thought that we want the y value of that point. Oh, well, then I'm going to take this x value and plug it into here, because that will give me the y value of that point. That's how high it rises. Okay, and you had the answers to these, so I won't worry about that. Okay, and then it said, how far did it travel, right, till it landed? So what do we know over here when it lands? Right? Remember we did some of this with parametrics, the same kind of thing. We want that to be 0. So we're going to put a 0 right there and do a solve on our calculator, right? Now it's going to give us 2 values because there's one back here and there's one here, right, when it's on the ground. We're going to want the one over here, right? Okay, so then what was part B? Was there a part B to that? Well, just draw the graph on your calculator. So you might have actually done that, right? So just draw the graph of that. Okay, so then we go to 21. And what did 21 ask for? So 19's kind of it's not really a global max. I mean, it is sort of. We found the highest point. So that is, if that's the path, if y is the height of the ball, we found its max, right? We found its maximum. So we didn't really follow the recipe so much there because, geez, they gave us the equation, right? So everything was below the red line. Did I check to see if the derivative was undefined? I guess I didn't. Did I do a list of candidates? Not really. But this one just felt a little different. I mean, I suppose maybe I should have, had a little bit of a discussion, but I think if I drew the graph of that, if I said something like, hey, it's an upside down parabola, there's just one highest point, you know what I mean? I would probably point out to you a problem like that, hey, be careful to do this or whatever. So I could see where you look at that and say, well, wait a minute, how come we didn't do that with following the steps and list of candidates and all that stuff? Okay, so we could have. We could have thrown that in there. But that problem just had a little different feel to it anyway. All right, so what's 21 about? What's this R business? What was that when you read that problem? Caleb, what was R? What did R stand for? What does that mean? How far it traveled. Okay, so here's the track coach part of it. Okay, so what they've done is they've rearranged as a matter of fact, this is what part A was about. Okay. So forget part A. Tell me what part B was about, Caleb.
It's in the V0 is fixed and it's variable. You want to find the value of that
That maximize the range. Steph, I didn't check your homework. You've got it. I'll check it for you. Okay, so tell me, in the football language, tell me what they're wanting you to do in B.
change the slope of the hill.
So they said V sub 0 is fixed. What's V sub 0? So we're going to kick at the same velocity every time, right? We're going to kick at the same, kick it just as hard every time. But we're going to change what? The angle. And to do what? We're going to change the angle to...
Maximize how far it goes.
Okay. So if you're a punter, you might want it to go farther, right? So as a track coach, I think of the shot put. I always think of the shot put when I think of this problem, right? Is anybody here throw the shot put? Okay. Does Coach Kitzelman ever talk about what angle you should throw it at? He doesn't say slope on that.
Yeah, like he wants it high, but never an exact angle.
Never an exact angle because, geez, you don't want to be thinking about that when you're throwing it, right? Oh, gosh, I threw that one at 37. I meant to throw it at 36, right? So it'll say it was too high or might have been too low, and we adjust, whatever, okay? But the idea is it might be nice to know, right? At what angle should I throw it to make it go the farthest, right? That's what this problem's about. Okay, I took a class in college, one of the hardest classes I took in college. Actually, the two hardest classes I took in college. Now, remember, I was a math major. Two hardest classes I took in college were both for my coaching endorsement, which you don't even need a coaching endorsement to coach, right? One was human anatomy, which at UNL, human anatomy was a class that all of the pre-med students took, and anybody in athletic training and everything ever had taken. I had to take it if I'd known. Looking back, I probably never would have done coaching. But gee, Christmas, I thought. Ask Mr. Limbach about it. We had the same class. We might even been in it at the same time. We didn't know each other. But looking back, we think we were maybe in it at the same time. But it was hard class. I mean, we did, our lab was with actual cadavers, and I still to this day remember going in for the lab exam on the nerves and, open up the cadaver and I swear to God, it just looked like spaghetti, and they were nerves, arteries, veins, and to me, they all looked alike. Every single one of them looked alike. And there'd be a little piece of string around one of them. There must have been 20. There'd be a little piece of string around one of them, and you had to identify it. So, any thoughts I had of being a doctor right then and there was out the window, which I had none, but because I was just kind of grossed out by the whole thing, actually. So, but whatever. That was one of the hardest classes I had in college, and the second hardest class I had in college was biomechanics for coaches, physiology. And we did these kind of problems. As a math guy, you'd think I would like it, but it was hard. But the reason it was for coaches is because long jumpers, right, or shot putters, or discus thrower, or football player, whatever, all of the physics that's involved with the various sports and those kind of things. And you know, how that would affect how you coach them and stuff like that. So this problem always reminds me of that. Now, I enjoyed it. It was interesting, but it was difficult. So anyway, we're trying to maximize. So part A in this, let me cover this up real quick. Part A in this says show how you can get that equation from the one in problem 19. Well, first of all, the range is how far it travels. So we're talking about at the end. Now, what did we say we know at the end when it lands on the ground? No, that's not what we needed here in part A. Okay. What did we say earlier? What do we know when the ball hits the ground, or whatever hits the ground? Y is 0. So we're going to take the equation in number 19, and we're going to put a 0 in for the Y. Okay? We're going to put a 0 in for the Y. And we want to solve for what? What was R again, Caleb? R was the horizontal distance. What's the horizontal distance in this problem? X. So the R is the X from this equation. So we're going to put a 0 in for Y, which is when it hits the ground. And then we're going to want to solve for X, because we want an equation for the horizontal distance. Okay? So X is what we want to solve for. So I'm going to put a 0 in right here. Okay? So I put a 0 on this side. And now I'm going to add this whole big chunk over to this side. Now, I could have typed this in my calculator and let it solve for X for me, but I'm going to do this one by hand because it's not that difficult. So I'm just going to grab this equation and I'm going to move it over to this side. Does that make sense? See what I did there? Okay, now I want to solve for X. Now, I know normally I would not divide both sides by X, but this time I'm going to, because the only time that would be a problem is divide by X if X is 0. Well, X is 0 is going to be this point back here. Do I care about this point? That's the point where I launch it from. I don't care about that point. But here's the one I'm looking for, that other X. So I don't care. So I'm going to divide both sides by X, which will make that go away, and which will make that just be an X, like that. Okay? Now, I could have done that before. I could have factored out an X before, but I knew I was going to do this. So I'm just dividing both sides by X. Now I need to get this X by itself. Well, I've got 3 things here, so I'm just going to divide by this one. So that'll move that over. So I just divided by 1 plus m squared. Because I want the m, because remember it said m is going to be our variable. We're going to change our slope. Unlike the number 19 where we let the slope be 45 degrees, we're going to change the slope. So that's actually our variable. And then I've got this fraction still sitting here. So how do I get that over there? Multiply by the reciprocal. So I'll just flip it. And sure enough, that's the equation that they have in number 19. So that's, or number 21. So that's how you do part A. Part A is just show how you can get that equation from, okay, but they gave it to you. They gave it to you. So again, you didn't even have to do the above the red line part. You didn't have to set up this equation. They did it for you. Okay, they just, in part A, they asked you, you know, show where it came from, right? So there's our equation. Now, v sub 0 is constant, right? Initial velocity, Caleb told us that, right? We're going to throw this shot put with the same velocity every time, okay? And gravity, of course, is constant. So this is just one big constant sitting out here in front. And what do you do when you do a derivative, which I'm sure at some point we're going to do a derivative here, right? What do you do when, you want to close that for me, Steve? Thanks. What do you do when you do a derivative and you got a constant sitting out in front? No, it just hangs out there, right? If you've got a constant sitting out in front of a function, you're going to do the derivative, it just hangs out there. So right now, I've got this equation, right? So here's my equation right here. Okay, so I've got my equation, I've changed my x to an r, and now I want to find what on this? Caleb, say it again. What do they want me to do in part B?
Find the value of m.
I want to maximize R, right? I want to find the max of R. So I need an R equation, which I got. That's what I just spent all this time doing. So now we're ready to go. But so we're below the red line. We're on step 4. I want to find the max of this, right? So how do we find the max of this? What's step 4 say? Find the critical points, right? Where's the derivative 0? Where's the derivative undefined? All that stuff, right? So I need the derivative of this, right? Need the derivative of this. So I need R prime. So this just hangs out here in front, and I do this. How do I do the derivative of this? How do you do the derivative of this? M is our variable, right? This is like our x. What? Yeah. I could move it up, but that would be more complicated, I think. I could do it. Yeah, I could use my calculator too. I want to do this one by hand. You could do this on your calculator. Quotient rule, right? Derivative of this, I got to do the quotient rule, right? So this is just going to hang out. So let's do the quotient rule. So the quotient rule would be derivative of top, which would be 1, bottom left alone, minus top left alone, m, derivative of the bottom, 2m, all over the bottom square, right? I just want to do it by hand because I just want to show it's easy. It's easy. It's an easy quotient rule. Look what happens here. This would be 2m squared. So I'd have 1 plus m squared minus 2m squared, which would be 1 minus m squared. Here it is over here. So the top is just 1 minus m squared. The bottom is this. And then I got this big constant just sitting out here in front. So there's my derivative. I want to see when that is 0. Well, this is not going to be 0. What's the only time this would be 0? What's the only time this fraction would be 0? If the velocity is 0. What would happen if the velocity is 0? It wouldn't go anywhere. You wouldn't even throw it, right? So that's clearly not what we want. So this is never going to be 0. And when will this be 0? When's a fraction ever 0? The top is 0, right? So this will be 0 when the top is 0, right? So 1 minus m squared. So when 1 minus m squared is 0. So that whole thing breaks down to just that, right? When is 1 minus m squared equal 0, right? And that would be plus or minus 1, right? And let's think about that. M was what again? The slope that we throw it at. So 1, we talked about that. That'd be 45 degrees. What about negative 1?
We'd have to dig into it.
Yeah, okay, so probably not going to throw it like that. Okay, so we can probably ignore the negative 1. So we've just found slope 1. That'd be like 45 degrees. Okay, what about r prime undefined? Here's r prime. When will that be undefined? When the bottom is 0. When will 1 plus m squared be 0? When m squared is negative 1, when will m squared be negative 1? Never, right? Never. You can't square do negative 1. So r prime is never undefined, so I got that down there. What about endpoints? What about endpoints? What variable am I looking at there for my endpoints? Right? We always say endpoints are when something's the smallest it can be and when something's the largest it can be. When what's the smallest it can be?
X.
There's no x up here. What's my x in this problem? The input. What's my input here? M. Right? Endpoints. Let me say it again. When you're looking for endpoints, it's whatever. You said x earlier, but there is no x here. It's input, right? What's the smallest my input can be and what's the biggest my input can be. And my input here is m. M. So what's the smallest m could be? M is my slope that I'm throwing. 0? Now, it's not going to go anywhere, right? If I throw it, right? Now, again, this formula is from ground level, so we're going to discuss that in a minute, right? Because I don't think Rachel throws a shot put from the ground, right? It doesn't lay down when she throws it, right? But so we'll talk about that being 0, okay? Now, so I suppose if I'm throwing from here, I could actually throw it down. So you could talk about it negative, right? You could go straight down. Let's call it 2. Let's say it's 2, okay? And then what's the biggest m could be? Straight up. What's the slope of straight up? That's undefined. That'd be like infinity, right? Slope bigger. You go past there, now it's negative, so it'd be infinity, right? I mean, so, probably don't want to throw a shot straight up. Right? Unless you're ducking, right? So, but those would be the things we're talking about. So if I'm going to make a list of candidates, that's what it would look like. Okay, so I'm ready for my list of candidates. I'm going to plug those into the original. So I'm going to put R of 0. Now, Jared in the other class asked this yesterday. It was a good point. He said, do you have to describe, do you have to show any work on your list of candidates and what you're plugging into? I said, no, your notation should show it. And the problem was he wasn't doing his notation right. This is your explanation of what you're doing right here. This tells me you're putting a 0 into the R equation. So make sure you put proper notation. Don't write F of 0 here. There's no F here, right? You'd write R of 0. And then we'd have R of 1. And we would have, then we would talk about as x goes to infinity. Okay, so let's put a 0 into R. So we put a 0 in here, we're going to get what? 0 over 1, which is 0 times this, that'd be 0. Okay, we knew that. It's not going to go anywhere. Now remember, we're throwing this from the ground, which is not that realistic. But at football, maybe that is, right? I guess it'd be more of a drop kick from the ground because you actually don't kick it. But I guess on a tee, right? We'll say it's on a tee. So we're kicking it from the ground. So for a football, this would be, shot put is not quite as good of an example because you don't throw from the ground, but we'll talk about that here in a minute. All right, so put a 1 in here. So let's put a 1 in here. So we get 1 over 2, right? So we get 1 over 2. The 2 would cancel this. And so you end up just getting V sub 0 squared over G, which is just some positive number, right? Both of those were positive. G was 9.8. You might say, wait a minute, gravity's negative. Well, they had that negative in the equation. So G is actually positive 9.8 here. And whatever your velocity is squared. So it's just some positive value. And then what happens as x goes to infinity, or excuse me, oh gosh, wow. Somebody should have yelled at me. We're not talking about x goes to infinity. We're talking about m goes to infinity here, right? We don't have any x on this problem. We have m, our slope. So as m goes to infinity, what happens to this? 0. The bottom's bigger. High powers dominate. So as n gets really big, this is the bottom. This is going to go to 0. That times that whole thing's going to 0. So what's my max? Which we kind of knew was going to be, is which one? R of 1. Yeah, so we should kick the ball at what angle? 45 degrees. Now, and Caleb, read the question to me in part B again. So we want to kick the ball at a 45-degree angle to maximize it. If we kick at the same speed every time and there's gravity, we want to kick it at a 45-degree angle every time. Okay, so now, let's go back to the shot put example. I've talked with Coach Larson before, who coaches the shot put for the boys, and I talked to him years ago about this, and I asked him if he ever talked about it, and he said, not really. He said, there's a lot of things involved. But he said what he had read, he didn't know the mathematics behind it here, what he had read is somewhere around 42 or 43 degrees was the maximum angle to shoot, or to throw the shot put. Around 42 or 43 degrees. He said, but it kind of depends. And so I was thinking about that. So let's talk about the example then of an actual shot put. So we said this should be 45 degrees to maximize this, right? But in the shot put, the person's more like here. Right? That's not bad. The shot put's more likely launched from there, from about 6 or 7 feet high, right? Well, if this is the maximum, if my picture is the maximum, 45 degrees right here, what's the angle up here? A little less than 45, isn't it? And what would it depend on then? How tall the person is, right? A shorter person would want to throw at what angle? A little higher than, would it be higher than 45? No, it'd be less than 45, but less, more of it higher than a taller person. So a shorter person would maybe want it a little bit higher, 44-ish, 43 degrees, and a taller person maybe 42. Does that make sense? Okay, so a taller person would throw a little flatter because they want it to be on that blue arc to maximize the range. Now, I asked him how much time he spent on that. He said not very much, because there are 3 things that determine how far this is going to go. There's gravity. Can't change that. So the only 2 things you really have to, as a shot putter, to control how far it goes is the angle you throw it and the velocity that you throw it at. Which one of those do you suppose has the most impact? The velocity you throw it at, because it's squared even, right? So if you really want to improve how far you throw it, you should what? Improve what? The velocity. And how do you improve the velocity? Get stronger, right? You get in the weight room. But not only that, but your technique, right? Maybe the spin or the glide or whatever you do, or as you move before you release it, all those things are going to affect how much power you can get into it. Now, you get to elite levels. You get to Olympic shot putters who maybe the difference between them is very, very small. And they're all about the same strength, right? They've all taken all the steroids they can take, and they've got, and they've all gotten as strong as they can get, and their technique is almost perfect and whatever. And there's this very small thing. That's when you get into the high-tech video analysis, right? And they might look at that, look at their angle, and they might be able to make some small changes in that angle that would give them those few extra inches. It might be a big deal. At the high school level, it's maybe not as big a deal. You can improve more if you change velocity, but it is a factor. It is a factor. Okay? So anyway, that's a good problem. But again, gave you most of the information. We could have done this derivative on your calculator. I'm okay with that, and it would have done that for you. But again, we follow those steps of what's going on. Okay, quickly now, let's talk about number 27. We already kind of talked about 28 yesterday, but I will just make a few comments about it. 27 says you have 100, what was it, inches, centimeters? Centimeters of wire. Okay, you have 100 inches of centimeter, or 100 inches of centimeter. I don't even know what I'm saying. You have 100 centimeters of wire, and you're going to make this box, okay? So the skeleton of a box. So the key element of this would be getting that equation over there on the right, okay? You know, when it comes to the quiz, so how much of this, so let's talk about the quiz. What do you need to be able to do? Well, we've done several box problems. I think that's a pretty basic thing. So rectangles, boxes, circles, you need to be able to work with these, okay? We want to maximize the volume, so we've already done this equation in number 28. Square base, so we get this again. But how many centimeters of wire are taken up? Well, you got 1, 2, 3, 4 pieces that are Y units long. So that's 4Y, and you have 1, 2, 3, 4, 5, 6, 7, 8 pieces that are X units long. So 8X plus 4Y has to equal 100. I mean, you just got to be able to come up with that sort of thing, right? And then that gives me that, which I substitute in for the Y right there. Okay, so I end up with this sort of equation for V. So there's step. Now we're down to the red line. There's step 3. Right? We identified, we're trying to find max volume. We got this, so we do the derivative. We set it equal to 0. I get those two numbers there. We can probably throw out 0. It's going to be one of our endpoints probably. Obviously, we wouldn't have any volume if X is 0. 25 thirds is the other one. The volume, V prime is never undefined because it's just a simple polynomial. And then our endpoints, what's the smallest that X can be? We said 0. What's the largest that X could be? That would be over here. That would be if Y, if we didn't have any Y at all, right? If we used all our wire here for the X. Well, you've got 8 little pieces that are X. So 100 divided by 8. So 12 and a half. So the biggest X could be would be 12 and a half. Okay? And so we plug those into the volume. Of course, both of those cases, we don't get any volume. Here, you'll get something. I don't know, plug it in back in here to V. I'll leave that for you. But you would just plug 25 thirds back into there, get that value. That is your max. Now, I think the question asked for the dimensions, didn't it? Okay, probably should put centimeters on those, which doesn't surprise us. It's a cube, right? We put that in. Probably, I would say you take your 25 thirds and you plug it back into this equation up here, right, to get your Y. So you got 25 thirds as your X, so go plug it into that equation, you'll find the Y. Okay, and it turns out to also be 25 thirds. So it's a cube. It's a cube. Okay? All right, so that's 27. Was there another part to 27? Was that the surface area part? Oh, here it is right here. I guess I got it. Okay, so now surface area, I might give you that equation, I might not. Surface area is just, was that the term they used, surface area? It's just this, the area of the surfaces, right? So what's the area of this front surface? X times Y. How many of those are there? There's 4 of them. Around back, on the sides, there's 4 of them that are that. And then there's the area of the top and bottom surface. What's the area of that? X squared, and the area of the bottom surface, also X squared. So your surface area is 2X squared plus 4XY. Okay, we have the same constraint with the wire that we had in the other problem, right, with the 100. So now it's just a matter of substituting that in place of the Y. You get your area equation is this, you do the derivative, and look at that, it comes out to be a cube also. It's the same thing. Once you get your H, so really the only thing hard about that was making sure you could find the surface area equation. But then you take that same constraint, plug it in, do your derivative, set equals 0, it's never defined, list of candidates, and away you go. Okay, 28, I'll just make a comment about the cylinder. The smaller cylinder, or excuse me, the cylinder that has the long side across would be that picture. Some of you had trouble doing that. Some of you just took the top cylinder hat and laid it down. And that's the same thing. It's just laying down. Okay? So the long side here is H. So it'd be the long side plus the girth. The girth would be the circumference, which is 2 pi r. And on this problem, the long side would be the diameter here. So the long side would be 2r. And then the girth would be the distance perpendicular to that. The distance around, which would be a rectangle. So it'd be 2r, h, 2r, h. So that's 4r and 2h. So it's the long side plus the girth there. So you get, and then I would solve for h. I think it's a lot easier, then you're not dividing by 2 pi and all that stuff. So just solve for h on both of those. Okay? And then you plug that in for that h, and you plug that in for h there, and then you're off and running. Okay? So then it's just, and the answer book's up here, so later on you want to check how you did on that one. And don't worry about part D right now. Okay? All right. Let's get your notes out, and let's move along here to the next thing. So that's optimization. There's more work to be done on optimization. I have nothing new to tell you about optimization. You got the set of steps. It's all about finding the thing you're trying to maximize, understanding what your variables stand for, getting the problem set up. It's just we need a few more days of practice. You need to be exposed to more problems and wrestle with them and try. Okay? Have more people coming in and asking questions outside of class, which is a good thing. Probably not as many as we need to have, but just broke it. Just fix it. All right. So here's the next thing we're going to be talking about. Related. Oh my goodness. Related rates. Okay, related rates. That is the name of this next thing. So we got parametric equations, we got optimization problems, max min, and we got related rates. Okay, so earlier in the year we used the basic definition of calculus as mathematics of change. We defined words that meant change: increasing, decreasing, growing, shrinking. Change occurs over time. So when we talk about how a quantity changes, we're talking about the derivative of that quantity with respect to time. Okay. So one of the main differences about this set of problems than optimization is our derivative is going to be with respect to time. We're talking, well, look at the name, related rates. We're talking about rates. We're talking about rates here. Okay, it's a little bit like the parametrics. It's kind of connected to parametrics. And there we were doing derivatives with respect to time too. We had x prime, we had y prime, or dx dt, dy dt. We were talking about how fast the horizontal, we had horizontal velocity, we had vertical velocity. Okay? Well, we're going to get into all other kinds of related rates here. Now, our first example is, well, we have a couple of examples here. Write the following, you don't need to write this down, just work with me here. Write the following statements mathematically. John is growing at a rate of 3 inches per year. Would you agree with that? Would that describe that situation? Okay, better yet, would that describe that situation? Right? dj, dt, or just j prime. Okay? So, my mutual fund is shrinking at 4 cents per day. You guys tell me what I could write there. F F for fund. Okay, if F is for fund, then I'll agree. Okay? Equals what? Good job on the negative. Good job on the negative. The fund is shrinking. It's decreasing. So F prime has to be negative. Or DFDT is negative 4 would be another way to write that. The radius of a circle is increasing by 4 feet per hour. I disagree. There we go. R prime. It's a rate. It's a derivative. Or dr dt. Notice these are all with respect to time. Per hour, per year, per day. The volume of a cone is decreasing by 2 cubic inches per second. V prime equals negative 2, or dV dt equals negative 2 would be how we would describe those situations. Agreed? All right. So let's look at this example. A rectangle is 10 inches by 6 inches, but its sides are changing. Think of it this way. Think of a rectangle. Wouldn't this be a rectangle whose sides are changing? Right there? Think of that kind of situation. Isn't it possible for both to be decreasing? Both to be increasing? One to be increasing while the other one's decreasing? Right? One could be increasing while the other one's decreasing? Right? All right, that's what we're talking about. A rectangle is 10 by 6, but its sides are changing. So in that scenario, tell me all the different things that are changing. Not only is the length changing and the width changing, what else? The area is changing, what else? The perimeter is changing, right? So the areas of this thing is changing, the perimeter is changing, and each of the sides are changing. That's what we mean by related rates. All 4 of those are rates. The side of the, so what could we write here? It says write formulas for perimeter and area and how fast each is changing. So let's say we had a rectangle where we had L and we had W. The rate that L is changing would be L prime. The rate that W is changing would be W prime. The rate that the area is changing would be A prime, and the perimeter, right? We would have 4 different rates, and they're all related, right? Because how fast the length and width are changing is going to determine how fast the area or the perimeter is changing. Make sense? That's why the name related rates. Okay? All right. So it says write formulas for both. So perimeter is formulas. 2L plus 2W. So what would the change in perimeter be? P prime equals 2L prime. Isn't that implicit differentiation? Right? You would do the normal derivative, but then you would tack on an L prime or a W prime, because we're doing it with respect to time, T, right? This is implicit differentiation that we're doing here. We didn't do that back in the optimization problems, right? Because step 3 was get it in terms of one variable. So when we did a volume problem, we got it in terms of X. Or we did the range problem, we got R, we got it in terms of M. So when we do that range problem, didn't we do dr? When we did R prime on that range problem, that was dr over, it was with respect to what? What was our input variable? It wasn't time. It was M. So in that problem, we were doing dr over dm, weren't we? Right? So we didn't have any M primes in that problem, right? Because M, right? We were doing the derivative of the range with respect to M, the slope, right? But here we're doing everything with respect to T. Okay, what is the area of the rectangle?
L times W.
Area equals L times W. So what's a change in area? That'd be A prime. That'd be what? That's a W. So it'd be L prime W plus L. It's not L prime W prime, right? What do you got to do? Product rule. You got to do a product rule. L times W. They're both, L and W are both changing with respect to T. We got to do implicit differentiation, just like we did on the gateway test. Got to do a product rule. Derivative of the first, L prime. Leave the second alone. Plus L left alone, derivative of W is W prime. Okay? So that's the kind of stuff we're going to be doing in these problems. Okay, now, what if they had said to me, the length and the width are both increasing at 2 inches per second. So as I'm dragging that rectangle, the length and the width are both increasing at 2 inches per second. What did they just tell me there? L what? They just told me L prime is 2. Remember what we did up here, right? And what else they tell me? Is 2. Right? So can I find the rate that the perimeter is changing? Wouldn't that be this equation right here? So it'd be 2 L prime plus 2 W prime, which would be 8 what?
Inches per second.
Inches per second. The perimeter would be changing 8 inches every second. Does that make sense? Sure, it makes sense, because as that grows, you have the length growing 2 inches every second. How many lengths do you have on a rectangle? How many lengths are in a rectangle? 2 of them. Well, if they're each changing 2 inches every second, your lengths are gaining 4 inches every second, right? Same with the width. So the perimeter is 8 inches per second. Okay? Now, what about the change in area? A prime. What would that be? Well, what would we put in place of L prime? 2. What would we put in place of W?
6.
Would you put 6 there? Okay? Because that's the instant in time we're talking about. Now, aren't those two things changing? The 10 and the 6 changing? Right? Isn't that rectangle growing? So, in a lot of these problems, they're going to ask you to find when is the area, what is the rate the area is changing at this instant in time. Now, they won't give you a time value, but they might say when the length is 10 inches, when the width is 6 inches, right? And that's when you'll plug in. So let's go ahead and assume that this is the moment in time we're talking about. Is right now the length is 10, the width is 6, and the length and width are changing at this rate. So you're right. We would put a 6 in for W. And what would we put in for L? 10. And what would we put for W prime? 2. So this would be 12 plus 20. That'd be 32. What would the units be? This is area now. So wouldn't it be square inches per second? No, you don't square a second. Now, why is that? Well, what were the units on this 2 right here? 2 is L prime. That's 2 inches per second. Times what were the units on 6? Inches. So don't we have inches per second times inches? That's square inches per second. Okay, and same thing. Now, I know in physics and science class, a lot of times they make you write the units on all your numbers. I'm not going to make you write your units on all the numbers. You have to have the right units at the end. Okay, if you want to write them, that's not a bad idea. 10 was inches, 2 was inches per second. So we get square inches per second. So at that instant in time, now notice we didn't have to use the 6 and the 10 here, right? So the perimeter was changing at the same rate all the time. Okay, now look at my example again as this grows. So what that means is if my length and width are both growing at 2 inches per second, that means my perimeter is growing at a constant rate. But is my area growing at a constant rate? My area is not, because what's happening as this grows, with every unit of time that goes by, I'm gaining bigger and bigger chunks of area, right? So the area depended on how big the rectangle was. So I needed those numbers in it. But that came from these formulas right here, okay? So that's the kind of stuff we're going to be doing. All right, let's take a look at an example problem from scratch, okay? Let's say, okay, here we go, right here. All right, so you might want to jot this down in your notes a little bit here on this one. So what would a problem look like from the get-go? An oil tanker spills oil that spreads in a circular pattern, and the radius is increasing at the rate of 50 feet per minute. 50 feet per minute. How fast fast are the circumference and the area of the spill increasing? And let's just do part A. How fast are the circumference and the area of the spill increasing when the radius of the spill is 20 feet? So it spills and it's growing and it's growing, and we want to know at the moment in time when the spill is 20 feet, the radius. Okay? All right, so I've got a circle. This is my oil spill, and it's growing. Okay? Now, tell me what I should write down. Tell me what information we have. Tell me what information I need, all that stuff. We'll just, before I show you the steps we would want to go through, let's just kind of throw it out there. Then we'll look at it.
Yep, R prime.
Okay, I like that. We know R prime is 50 feet per minute. Right? So you notice in these problems, what's different about these than optimization is the rates that are in there. You're going to see words like increasing and decreasing and growing and changing, right? That's not what we saw in these other problems. We were saying find the maximum volume. The word max and min was in there a lot, right? But you're not hearing that in these problems. You're hearing talk about increasing and decreasing, rates, that kind of stuff. So they're going to be very different problems from that standpoint, okay? So you shouldn't get that confused. All right, what else? What'd you say? R is 20. Okay? What else should I write down? The equation of what of a circle? Area of a circle is?
Pi r squared.
I agree. Okay? Circumference of a circle is 2 pi r. I just realized I forgot something. I told you I didn't talk about this. Come back to that later. Okay, anyway, let's keep going. 2 pi r is the circumference. Okay? Now what? Think about all that stuff we were doing before. Plug what into where? Plug R in? No. I'm glad you said that, though. Because that is a very common thing, and one of the things that they've got a different set of rules than I have. I'm not sure if we want to follow theirs, but I'll show you what they mean. What they say is to make a table. Don't write this down yet. We'll talk about whether we think this is a good idea. And on this side of the table, we put all the things that are constant. And on this side of the table, we put everything that's variable in the problem. Because things are changing in these problems. But sometimes things don't change. Like, for example, what in this problem is never going to change? Okay. Right. 2 is never going to change. I mean, right? Pi is just a number. I mean, obviously, those things are not going to change. But okay, what else? R prime is not going to change in this problem, right? R prime equals 50. That is constant. That's never going to change. Okay, what's variable in this problem? R is variable, right? That 20, right? Maybe so we're only write 20. R is variable, right? Because this is growing. This is growing. So anything, what they say is anything that's in the variable column, do not plug in until the very end. Now, yeah, let me go ahead and put that R equals 20. So we do not want to plug that in until the very, very end. Okay? Anything that's constant in the problem, we can go ahead and plug in whenever. But anything that's variable, we don't want to plug in. Okay? So what should I do next? So there's nothing more to write down, really. So what should I do next? Derivative. We need A prime, because what we're asked, how fast are the circumference and area changing? So we're asked for C prime, and we're being asked for A prime. That's what we need to find out. Right? So we do it just like we did up above. So what is A prime? So A prime would equal, remember this is dA dt now, we're doing the derivative with respect to t. Right? Okay, what is the derivative of pi r squared? Pi is just a number, it's just going to hang out there. We bring the 2 down in front, be 2 pi r. No. What's a normal derivative of r squared? 2r, and then tack on an r prime, right? Just like we did when we did implicit differentiation. So it's going to be 2 pi r, r prime. 2 pi r, r prime, right? Implicit differentiation is what we're doing here because we're doing derivative with respect to t. Okay, what about c prime? 2 pi is just a number set down front, right? So what's a normal derivative of 2 pi r? 2 pi. Tack on r prime, right? 2 pi r is just like 6 something times r, right? What's the derivative of 6r? 6, right? Tack on r prime, right? We had this same difficulty back when we were doing the gateway test. We would screw this up. If we have 6y, what's the derivative of 6y? 6 y prime. But if it's 6y squared, what's the derivative? 12 y prime, right? You do the normal derivative, then you tack on the prime. Okay? So the derivative of 2 pi r is 2 pi r prime. Okay, now we can plug in these things here. Now we've taken the derivative, we can now plug in this stuff. So over here, a prime is 2 pi. What do we plug in for r? 20. What do we plug in for our prime? 50. Over here, 2 pi. What do we plug in for our prime? 50. And we got everything we need. So this would be, what would that be? That'd be 1,000, 2,000 pi. What are the units? Careful, this is A now, this is area. Square feet per minute. And on this one, this would be what, 100 pi? And this is circumference, so would that just be feet per minute? That's what a problem would look like from the beginning.
Would you want us to leave it in terms of pi?
That's fine, leave it in terms of pi. You could go to a decimal. If you go to a decimal, make sure you do 3 decimal places. I would say don't go to a decimal. That's just another chance to screw something up, right? Leave it in terms of pi. That's great. Yeah. Leave it in terms of pi. Now, this would probably be a calculator one. The calculator will leave it in terms of pi also. So I would say just leave it in terms of pi.
You said we didn't have to do the table.
No, I don't think you do, right? But I think you do need to identify those things that are changing, and you got to make sure and not plug those in until the end. Now, it turned out we couldn't plug our prime in until the end anyway. Okay? But what would be an example of something where it doesn't change? Well, here would be an example. Let's see, do I have a picture of it? Right here. Okay, got this ladder sliding. Now, what are all the things that are changing in that problem as the ladder slides? What are the obvious ones? Y and X are changing. What else is changing? The area of this triangle is changing. The angle right here is changing. The perimeter of this triangle is changing, right? There's all kinds of things changing. What in this problem never changes? The hypotenuse, right? Never changes. So when I set up this equation, I would probably set up something like x squared plus y squared equals 6 squared. It would be okay to put a 6 in there. Like right here, it says, what about when the ladder is 5 meters up the wall? Some people would want to plug a 5 in for that y. You would not plug a 5 in for that y, not till the very end, because it's changing. The y is changing, but the 6 never changes. Now, other people would just set this up as x squared plus y squared equals z squared, and that'd be fine. And you could do your derivative from there. What's the derivative of x squared? 2x x prime. What's the derivative of y squared? 2y y prime. What's the derivative of z squared? Z prime. Right? But now, what is z prime? Z is the hypotenuse here. What's the rate that z is changing? 0, because it's not changing, right? Z is not changing as that ladder falls. So it's 0. So what happens? This side, whole side ends up being 0. What's going to happen down here when you do the derivative? What's the derivative of 36? 0. So either way, it's going to be the same, right? But the difficulty with this up here is you have to recognize, oh, there is no z prime because that's constant. You see what I mean? So that's what they say is if it's constant, you can go ahead and plug it in right away. But if it's changing throughout the problem, you do not plug it in until at the very end after you've done your derivative and everything else. All right, while we got our notes here, let's go ahead and go to those and just write down our steps. So let's see what they have for steps here. They say, okay, step 1. Now, you don't have to write all this out. Make a sketch. Okay, label all sides in terms of variables. Now, they say even if you are given values for those variables, I would probably leave that off. That's because where they make that table. I would just say label all sides in terms of variables. Okay? And at this point, I think is when you can decide for yourself, okay, is this a variable? Variable means to vary, to change, right? In the latter problem, the hypotenuse wasn't changing, so technically it's not a variable, right? So you could plug that number in. So that's important. Now, step 2 is the part, I don't know that you need to write this down. It says make a table of variables. One side is variables, one side is constant. So you have the variable column, the constant column. Now, they also talked about, when you're talking about increasing, decreasing, another thing to keep in mind is if it's decreasing, it's negative, like we talked about at the beginning. So make sure you do that as well. Okay, so I think that would be my step 1. Step 2, I think, would be this. Find an equation that ties the variables together. Pythagorean theorem is often a good one. Area, it says if it's an area, like we were doing area of a rectangle, we were doing perimeter, we did an area of a circle, we did circumference of a circle, and then we just looked at the latter problem, we did a Pythagorean theorem. We did x squared plus y squared equals 6 squared. Those are going to be very common types of equations we'll use in these problems. Find some sort of equation that ties all those variables together that are in your problem. It's usually going to be fairly obvious. Now, in the latter problem, if Jamie mentioned the angle was changing. What if the question involved the angle in a right triangle? What kind of an equation would you maybe come up with? And it was asking you about this and this. What kind of equation could you come up with that would involve y and x and also have theta? Tangent. Wouldn't tangent have all 3 of those in it? Tangent of theta equals y over x, right? So you might have an equation, a right triangle trig equation. That's somewhat common as well. Okay? All right, now their next step says you can plug in any variable in the constant column, right? I mean, yeah, that's fine. Don't write that down. Let's, we'll kind of compare this to my notes that I have here a little bit. The third step would be differentiate your equation with respect to time. You are doing implicit differentiation, right? I don't know if you need to write that part down, but that's what you're doing. We're doing the derivative with respect to time. So we're, yeah, the first part, differentiate your equation with respect to time. Yeah, I think you can write that down. Okay? Because I just showed you, you can plug values in at this point as long as they're constant. I mean, that's fine. Okay? And we can add to that. Now, so that's really your third step. Differentiate with respect to time. So these problems are going to have primes all over the place, right? We saw it. A prime, L prime, W prime, R prime, H prime, X prime, Y prime. You're going to have tons of that. Okay? Next step. Plug in all your variables. After you've done the derivative. And you've got your primes in there. That's when you can start plugging stuff in. Now you can start plugging all the stuff that you have. Now, I don't think you have to write that whole paragraph there. I think plug in all your variables. Now, what's it say? It says, hopefully you will know everything but one. Hopefully you'll get to plug in everything but the one you're looking for, and you'll be able to solve it. Now, sometimes you don't. Like on that ladder problem. On that ladder problem, they said when the ladder was 5 meters up the wall. Well, that would be y. So they just told you when y is 5, so you're going to plug a 5 in for y, but you don't have x. Could you get x, though? If you know that's 6, and now you know that's 5, wouldn't you be able to get x, right? Because on your paper, you've got x squared plus y squared equals 6 squared. right? So you could now plug a 5 into there to find x, and then that would allow you to put it in there. So it says, if you don't, you will need an equation which will solve for the unknown variables. Many times it's the same equation as the one you used above. So like in this problem, in the latter problem, we did the derivative of this. We had 2x prime, 2y prime. So usually that equation's already there. You already have the equation you need to find any missing pieces. Okay, and then the last one says label your answer. Okay, label your answers in terms of the correct units and make sure you've answered the question. Label your answers in terms of the correct units, very important, and make sure you've answered the question. Okay, so related rates. So you have a problem where there's a bunch of quantities that are changing all at the same time, and you can find out how fast other quantities are changing. The key to related rates, of course, is implicit differentiation. All right, so let me go back to my notes, and I don't have those in here, so let me pull those up real quick. Okay, here's what I had said. Let's see how it fits. Number one, identify all the various amounts, distances, rates, and the problems. Step two, I said draw and label the diagram. Well, those two were combined into one step on their thing. Draw, sketch, and label. Draw, sketch, and label. Now, what I said is identify the various rates. So sometimes when I read a problem, I hear circumference. Oh, I got to write a circumference equation. Oh, I got the length and width, L and W, whatever. Okay, so sometimes you identify them right away, but those kind of go together. Okay, their next step was write an equation that relates those different amounts. That's what we had for step two. Write an equation that relates those, right? Now our next step on 3 is 0 down, differentiate both sides with respect to t, right? That's what we just talked about. And then in step 5, I said substitute the given values. That's what we said in step 4, right? Plug in your variables, plug in your stuff, okay? And then number 6, answer the question. I put down here, check for the correct sign, units, all that stuff. So what I have here is pretty much exactly the same thing we just said for that. Okay, related rates. All right, go ahead. I'm going to give you a little bit of work time here. So let's get out your business packet. I wanted to make one comment about those problems. I forgot to do that when we were going over homework earlier. So on our homework, we're going to do a combination here of things. So in the business packet, all right, so we're going to go off the script here a little bit on the assignment sheet. The business packet. Yeah, anybody else that doesn't have one? Yeah, come on up here. Okay. All right, so the problems are in the back of the book. So let me talk about number 3. So number 3 said to find the number of units that produces a max revenue. So this is very simple. They gave you the R equation, do the derivative, set it equal to 0. It's never undefined, but it's an upside down parabola. It's very simple. It's going to be your maps. Do a number line maybe, list of candidates. They don't really give you endpoints. You can do a list of candidates, whatever. Find the max. Okay, 8. Here's what I did not see, I don't think, on most of your papers. They gave you the C equation. But what did they ask you to find the minimum of? C bar, cost per unit. What was C bar? We had this in the notes yesterday. C bar is C over X. So what you needed to do is take that C equation and divide it by X. That is C bar. So you got to take the C equation and divide it by X. And then that's what you're going to do the derivative of. So you'll get C bar prime equals something, something, set it equal to 0, and you go from there. Looked like most of you on your paper just took the C equation that they gave you and went from there. C bar is the cost per unit. So you got to take the cost equation and divide by X. Just put that into your calculator that way. It's fine. Okay? All right, so be careful on that. All right, so what your assignment is then, in the business packet, okay? So in the business packet, we're going to do the rest of the circled problems. So when I say finish the business packet, I'm talking about the circled problems. So we already did 3 and 8. So that leaves you 10, 12, 13, 15, 19, and 20. So those are max min kind of problems. So that's why I was telling you we're going to be doing some of both. So that's max min problems there. And in 4.5, just to kind of get started on this idea of related rates, we're going to do 4 and 7. Okay? Now, I want to help you get a start on number 15. I'm looking at how much time we have left, and there's not a ton of time to get going here. So let me help you get a start on number 15 in the business packet. Okay, so that's the assignment. These are max min problems. These are this new thing we talked about today, which is related rates. All right, so 15 says a commodity has a demand function modeled by, now that's a lowercase p, (100 minus 0.5 x squared), and has a total cost function modeled by 40x plus 37.5. What price yields a max profit? Okay, so let's talk about this idea of what a demand function is. Demand determines what? How greatly the product is desired or sold or whatever. That's what demand means, right? The demand. So if you have a high demand for a product, what does that usually mean? The price can go up, right? They can raise the price of it. And if you have a low demand, the price can go down. So price is something that in most scenarios in business changes. Price is usually not a fixed amount. So where did we talk about price in our notes the other day? If you just turn back one page, right? Where did it talk about price there? Wasn't it in revenue?
Revenue minus cost.
No, we had revenue minus cost. That was something different. Step. Revenue minus cost was different. That was profit. Profit was revenue minus cost. Well, yeah, price per unit is P. Where's that in that little table? Isn't it in the revenue section? What do they have for little equation for revenue? They have X times, no, it's not profit though, it's little p. What's little p?
Price per unit.
Price per unit. Remember yesterday when we wrote this up, we said revenue was, the way we wrote it was, we said it was number of units times, what did we say? Price per unit, right? That's for us was revenue. Okay? Well, the price per unit's not typically going to be just a number. It's going to be an equation. That's called the demand function. That's little p. Because it's going to change. Little p is going to change depending on x. It's going to change depending on how many units we make or sell. You see what I'm saying? So little p is usually going to be an equation. The price per unit, because number of units is usually x, right? Price per unit is going to be an equation. And that's where you get this x times p. So that's one you probably better understand, like in your notes or whatever in a problem. Okay? I mean, if you just understand that it's number of units times price per unit, that's fine. But when they call it the demand function, you gotta know what that means. Okay, so it's little p. All right, so they want us to do the max profit. Now remember, a profit, that's big P, was revenue minus cost. So, think about our steps now. Okay, now we got related rates, so we gotta make sure we're thinking straight here. On optimization, we want to do max profit here. What's step one? No, that wasn't step one.
Oh, identify.
Identify what we're trying to maximize. So what are you trying to maximize?
Profit.
Profit. So right away, big P equals. That's where I start. Right? Now we know from up here, what's our profit equation? Revenue minus cost. Well, what's revenue? Revenue is X times price per unit. Well, what is our price per unit? 100 minus 0.5 X squared. Right? There, and that, now that's just our revenue right there. Right? That's our revenue. Minus the cost, which is that there. So that is how you build a profit equation. So profit is revenue minus cost, and revenue is typically this right here, X times little p. But I don't want you to memorize that. I mean, great if you do, but I also want you to understand it. Little p is the equation for the price, because that's going to change depending on how many units we have. So we have a price equation. So number of units times price per unit gives me revenue minus cost. There you go. Now I got my profit equation. Now we're to the red line. Right? Now we can find our max profit. Right? Now we're ready to find our list of candidates, do the derivative, set equals 0, on and on. Make sense? Okay. That's what, because the two business problems we did for today were just simple. They were just, here's the equation. Although that one you did have to do C bar. You had to recognize you had to divide by X. Okay. But here's what a profit one, a typical profit one kind of looks like. Okay? All right. So there's your homework. Got some of these in the business packet, and then 4.5, two problems that are the rate kind of problems, like we did today.